and I will share my screen and we'll get to work. Okay, and I'll just remind you guys all that next Thursday, so a week from today, we don't have class because I'm moving that day. So we are canceling that day for both. I know Aaron's in both Quantum 1, Quantum 2. Okay. All right, this is where we were last time, right? So we were talking about the momentum space. Oh, sorry, I gotta get on the right layer here. The momentum, we ended up with a momentum space eigenfunction here. And we already know and love the position space wave function. And we notice that they are actually the Fourier transforms of each other. And actually, one of these should be, yeah, this is a little bit of a typo. Let me see. Hold on. Gotta fix it. Yeah, this one should be a positive. There we go. Positive IP x over h bar. Wait. No, I messed that up. Give me a second. I didn't write down the two Fourier transforms, which I should have done. Okay. This is negative, but I got to write down the two Fourier transforms. It would be a little better for you. Okay. So we'll write them down over here. So so we have that the phi, so this is the momentum space. It's a function of the momentum and the time, not the position and the time, but a momentum and the time, is the Fourier transform of the position space waveform. So it's e to the minus I p x over h bar, sorry, x over h bar, and then the position space wave function. And then you're integrating over x, right? So there's a px. This is, let me erase that and do a little better job of that. I'm sorry, this is a little too messy for you to read. So e to the minus I p x over h bar. Okay, so notice we're integrating out x. Once we integrate over this, there'll be no more x's left, but only p's. Okay, so so that is the momentum space wave function. And then to get back to the position space waveform, wave function, which is only a function of x and t, it's the inverse Fourier transform. So 1 over square root of 2 pi h bar, and then the integral from minus infinity to infinity of e to the positive I p x over h bar, and then you put in the momentum space wave function. And you integrate over all the p's. So now you've gotten rid of all the p's by integrating those out, and you're left with x. So this is the Fourier transform and the inverse Fourier transform. Okay, so these things are related by their Fourier transforms. And I hope that makes a tiny bit of sense, maybe, because think about a Fourier transform. A Fourier transform takes you, let's think about it in music, right, or sound. It takes you from position, from time to frequency, right? So those two variables. Similar here, it takes you from position to momentum, and momentum is kind of like a wave, you know, like the de Broglie wavelength is related to the momentum, right? So it's kind of a very similar idea between these two variables. Okay. All right. And again, like we had with the position space waveform, so I'm going to put that up here. I know we're running out of room up here, but I just want to close out this little piece. So when we have the probability, so the probability of finding particle between x and x plus dx is equal to the the psi star psi, right? And then the probability of finding the particle's momentum between P and P plus dP is the phi star phi, dP. Okay, so they play a very similar role, right? So this you would use phi squared, phi star phi for a probability distribution of momenta, right? Okay. Let me know when I go to a new layer. Layer or no? Yeah? Okay. All right. So now we're going to, let's calculate. So let's calculate the expectation value of x. And we're going to now do it and see how that's related. Well, see how this works in the momentum space. Okay, we're used to dealing with it in the position space, but we're going to do it in the momentum space. Okay, so first we're going to start with our expectation value of x in position space. So I'm going to do my usual integral of psi star psi. So this is the position space waveform sandwiched with x in between the two, right? dx. Okay. But now I have a formula from the previous page for how to go now, how to write psi in terms of big phi just using Fourier transforms. Okay, so I have now the integral, so this is equal to the integral, and now I have a bracket, okay? And I'm going to put the Fourier transform in here, and actually I'm going to use a different color because it's going to get a little ugly. So we're going to go 1 over the square root of 2 pi h bar. And then the integral, this is going to be our psi star. As a matter of fact, I'm going to put that guy in green. Okay, and this is going to be the integral e to the minus I p x over h bar. And I'm going to use a prime on this p, and you'll see why in a minute. And then phi star of p prime and t. And of course, integrating over all p prime, okay? And then I have, give me a second here. I'm gonna erase this for a minute. Okay, and now I have another one, right? I have this psi, this momentum space wave function, and so I'm going to have an integral, another integral. So we have the integral of, whoops, I forgot my 1 over square root of 2 pi. Better there's some room for that. So 1 over the square root of 2 pi h bar, integral of e to the I px over h bar.
Yes, you also have to multiply it by x.
Oh yeah, thank you. Yeah, let me move this now since I'm. So x, not times, but x, right? And then we have our 1 over the square root of 2 pi h bar, the integral e to the positive I p, not p prime, right? We're using a different value here just to distinguish the two integrals, right? And then phi, not star, right? Because this is from psi, here, the blue psi, of p and t, and integrated over all p, right? And then I have to end my bracket, and I have a dx, right? Like that. Okay, so we now have these two Fourier transforms here, right, that we now have to deal with, right, because we're trying to convert to momentum space. All right, but I want you to notice something. Notice that x times e to the I px over h bar, we can write as this, minus I h bar d dp of e to the I px over h bar, right? So prove that to yourself, right? That if you took the derivative with respect to p, right, you would get ix over h bar. Right? The two i's would make minus 1, and the minus sign would cancel that. The h bar would cancel the h bar that you get on the bottom, and you'd be left with x e to the I px over h bar, right? Okay. So we can now work on the blue integral, right? So let's work on blue integral. So we're going to take the blue integral out. Well, first I'm going to write my x. So let's take the second part of this up here. So second part integral. So we have x, and then we have the second integral, which is the blue integral. Right? That's our second integral. It has, and we're keeping the x in there too. Now I can pull this x inside, right? So when I pull it inside, I'm just going to make it blue. So we're going to say this is 1 over, the reason I can pull it inside is that it's integrating over dp, not dx. So x is like a constant in that integral. So 2 pi h bar, and then we have the integral x e to the I px over h bar, and then our phi of p and t dp. Okay, now I know I just said that this is this, right? This is this stuff. So I'm going to put that in. So we have equal to, so this is equal 1 over the square root of 2 pi h bar. And then we're going to put minus I h bar dp of e to the I px over h bar. And then we have our big phi of p and t dp. All right, now I can pull some of this stuff out. But anyway, I'm going to pull some of this stuff out, but I'm also going to integrate by parts, right? Our favorite thing to do. We're going to take the derivative off of this term here, the e to the IPX, and stick it onto this term, the phi. All right, so I'm going to do that. I'm going to get that, gets rid of my minus sign. So I'm going to get 1 over the square root of 2 pi, let's say square root of 2 pi h bar. And then I'm going to get rid of the minus sign here, right? So I have a positive, give me a second. I feel like I missed an h bar. I missed a sign somewhere. No, it's okay. Okay, so then I have positive I h bar. I'm just going to pull that guy out. And then I have the integral e to the I p x over h bar. And I'm going to use a partial derivative now because this is phi. So technically I got to use a partial because phi is a function of p and t, right? So partial p dp. Okay, and I'll rewrite it one more time to 1 over the square root of 2 pi h bar um, and uh, integral of e to the I p x over h bar times negative h bar over I, because I'm just bringing the I down, partial p acting on this phi. I'm writing it a very particular way for a reason. Okay, so notice this might look a little familiar, right? That the that it looks a lot like our our operator form of p, right? And I feel like I'm missing a minus sign, so let me just check something real quick, because I do still feel like I'm missing a minus sign. I don't know why. Yeah, okay, yeah, that's right. Never mind. Okay. So we're not done, right? We're not done. So let's just keep going. So we did change this part of the integral, this guy, right? All right. So now what? Now I'm going to collect all the integral signs over to one side, okay? And so I'm going to go back to my pink color and start working with the full expression. So we have this. I'm going to pull these two square root of 2 h bars out, so to give me the 1 over 2 pi h bar. And then I'm going to have three integral signs, 1 over dx, 1 over dp prime, and 1 over dp, right? And inside I have a bracket. And I have the, now everything's in one color now. So e to the minus I p prime x over h bar. And then I have my big phi star of p prime t. And then I have e to the positive I p x over h bar, and my minus, so I'll put a bracket here, minus h bar over I partial p on phi of p and t. And then all my little differentials, dp prime, dp, dx. Okay. Yeah? All right. I guess I didn't need the bracket. All right. All right. So now let's take a look. We know there's a really interesting thing here, and that is the x integral, right? The only thing that has x in it are these two pieces right here. And remember, that's being integrated over x. Here's our dx, right? Okay. So, but if we look at that x integral, right, there's nothing else that has an x. So we can just kind of do it on its own. So the x integral by itself, I'm going to have here in green. So the x integral is the integral e to the minus I p prime x over h bar, and then e to the I p x over h bar dx. Well, let's write that again. So e to the I x, and then p minus p prime over h bar dx, right? Okay, so if we let's just do a little change of variable here. So we're going to let I'm gonna show you what this integral is in a sec, but I gotta do a little change variable. So let's let y equal x over h bar, and dy then is going to be dx over h bar. Just need to get rid of that pesky h bar in that integral, and I have to get rid of it for a reason. Okay, so I'm gonna now do my, so I get 1 over h bar, right? And wait, is it 1 over h bar? No, sorry. Oh, so it's h bar. H bar on top. And then I get the integral e to the I y p minus b prime dy. Okay? This thing here is the definition of the Dirac delta function. This is equal to 2 pi times delta of p minus p prime. Oh, and I forgot my h bar. 2 pi h bar, right? P delta p minus p prime, because this thing is a delta function. Okay, so if we do that integral first, what are we left with? So first of all, we're going to get the 2 pi h bar canceling out, so we're not going to have this. So let me write my thing one more time. So I'm going to go back to pink, or purple, whatever that color is. So there, that's more pink. So now we have 2 integrals left. We're going to cancel out the 2 pi h bar because we have that here. That's going to cancel out. So no 2 pi h bar. We only have 2 integrals left, not right. Right, because we already did one of them. We did the x integral. So we have 2 integrals left. So 2, 1, 2. The e to the I, p, x's and stuff are gone. And what we have left is phi star of p prime and t with this, weird minus h bar over I operator thing, partial p, which I said it's an operator thing for a reason. I'll get back to that. And then a dp, oh, sorry, my delta function. Forgot about him. Okay. Delta of p minus p prime, dp dp prime. Now again, just like when you have a Kronecker delta, right, and you have 2 sums, this is a delta function, Dirac delta function, and 2 integrals. It gets rid of one of the integrals, just like the Kronecker delta with 2 sums. You get rid of one of the sums. Similar thing here. And let's just choose to make every p prime a p. Why not? Okay. So I get phi star of pt times this minus h bar over I d dp phi of p and t dp. Okay, so notice we have 2 representations now, right? So if we think about it, this is the expectation value of x up here, right, where we sandwiched x between 2 wave functions that were written in terms of the position, right? And the operator for x that we sandwich between is just x. However, in momentum space, here, the operator that represents x, or position, is not just x. It's this thing, minus h bar over I ddp. So if we write down, remember what we had the p hat operator is h bar over I ddx. Actually, let's be a little more general and use the partial derivative form, because that is more general, right? So h bar over I partial x in position space, right? But and x. So let's write x here. So x hat is just x in position space, right? But in momentum space, p hat is just p in momentum space. And x hat is minus h bar over I partial p. Okay, so there's this equivalence between, the position space, guys, and the momentum space, guys. Now, we haven't proven that p is just p, but that hope it makes logical sense that that's what it would be, right? Any questions on this? Nope. Okay, I need to get a new layer. Are we good? Okay. All right. So now let's switch gears. We're still in chapter 3. And we're going to be in chapter 3 for probably the rest of this lecture for sure. Yeah, definitely. Okay. And we're going to look at the uncertainty principle. Now, you all know and love the uncertainty principle that we've had, over and over again, right? You've had the and in 251, you probably saw it like this: delta h, delta x, delta p greater than or equal to h bar over 2, right? In quantum 1, we showed you that this is actually not some delta, but the standard deviation of the distributions in x and p, or times times the standard deviation of the distribution in p, have to be greater than h bar over 2, right? So this is what we see in quantum 1. But I'm going to show you something that this actually comes from a much more general calculation that really is not just about x and p, but about any two variables. Okay, so we're going to two observables. So we're going to do a calculation of a general uncertainty principle that can be applied to any variables, any two variables. Okay, so let's do that. All right, so general. So we're going to now do the general calculation of uncertainty principle. So this is like Phys 251, and this is Phys 302, and this next one is Phys 474. Okay, so let's start. So let's remember that we have, let's say we have two variables. So say we have two observables. Remember, that means they're Hermitian. A and B. And they're represented by their operators, right? A and B. So they're both Hermitian. Okay. Then I can write down what sigma A is. So sigma A squared, so the variance, right, is, as we know, it's the expectation value of A minus subtracting off the expectation value of A, right? So the mean, subtracting off the mean and squaring the differences and taking the average. That's what sigma is, right? But I can write this now in my Dirac notation more, using Dirac notation. And I can write this as, pick some psi, so some psi here. And I'm taking the expectation value, right? That's this stuff here, of the stuff inside. So it's A minus its mean, right? Squared acting on psi. And all of these should have hats, but I'm going to leave the hats off because they're just, well, maybe I should keep them. It's too confusing if I don't, but it's a pain to keep writing hats on everything. Now remember, the expectation value here is just a number like 3, right? So It's this operator here, A, that we worry about. Okay, so now we have two of these, and I'm sorry, I forgot the other part, ket part. Okay. All right, so now I can take one of them out. This is a Hermitian operator, right? This A is Hermitian, so that means that A minus its mean is Hermitian. And so I can move one factor of A hat minus expectation value of A to the other side. So, because that's what hermiticity means, right? Okay, so A hat minus A on this side with A hat minus expectation value of A on this side. Okay. Okay, and I'm going to define this. I'm going to move my screen over a little bit. Okay. Actually, move you guys over a little bit. Okay, there we go. I'm going to define this as F inner product with F. Okay, why? Because these are the same, right? F and F. Okay. I can do the same thing with B. Right? So, sorry, this should be the equal sign. Sigma squared B is, of course, the expectation value of the deviance from the mean. B hat minus expectation value of B all squared and expectation value. Write that in ket notation. Again, with a psi. And we have B hat minus the expectation value of B, squared acting on psi. Because B is Hermitian, we can do exactly the same thing, and we write B hat minus expectation value of B acting on psi on this side, inner product with B hat minus the expectation value of B acting on psi on this side. And we're going to define that as G inner product G, right? Okay, so this again is, this guy is G, right? G inner product G. And that's just because it's going to get nasty. All right. Now, back in quantum 1, you may remember there was like a problem. Maybe we didn't do that problem. I can't remember exactly, where we proved what's called the Schwarz inequality. And that looks like this. So if we have for sigma A squared, sigma B squared, if we multiply the two of them together, we get, because remember, we were after this, right? So we mount the two of them together as a sigma B. Okay. This would be F inner product with F times G inner product with G. And the Schwarz inequality says that this product will be greater than or equal to the inner product of F on G, okay, squared. Okay. Now remember that squared means like F inner product with G star times F inner product with G. Okay, that's a Schwarz inequality, and we're going to be using that. Okay. All right. So let's think about this. So if we have a complex number, and that's what the Schwarz inequality is. That's why you have these bar squared, right? That's the complex conjugate times the number. So if we have something like Z, so this is a complex number. So if we have complex number Z, right? So then we have Z squared. We know that it's true for any complex number that the real part of Z squared plus the imaginary part of Z squared is greater than or equal to the imaginary part. of z squared, right? So think about that, right? If you have a complex number like x plus iy, if you square both, so now if you have x squared plus y squared, that's in general going to be either equal um, uh, to y squared or greater than it, right? Make sense? All right, so that's true for any complex number. Okay. So, but we know that we can write the imaginary part of any complex number like this: 1 over 2i z minus z star. Okay. Um, so think about why this is true, and I want you to take just 3 minutes to prove to yourself. Write z as x plus iy and prove to yourself that this is true. Okay. Question?
No, it's just that. Never mind.
Are you okay?
Yeah, it's just I had, I guess, the answer, but
Yeah, I just want you to prove to yourself that you can get that. You can prove that's true.
okay.
So just everybody let me know when they got it. Got it, Haley?
I'll be honest, I was catching up writing and I missed the question.
Okay, the question is just prove to me or prove to yourself that this is true, given this. How's everyone else doing? I see Jackson. I know Haley's still working. Hello? Aaron, how are you doing?
I'm working at it. I went to the bathroom in the middle of that, so I was kind of I'm a little lost.
Okay. Well, I'll give you 2 more minutes, then we'll just go over it, okay? let's go over it, guys. It's really not too hard, so let's look. So we're gonna take imaginary z. So we're gonna take 1 over 2i, and then we're gonna use this z, not 2 pi, 2i, and we have x plus iy minus x minus iy, because that's the complex conjugate, right? And that's 1 over 2i, and then we have x plus iy minus x plus iy, right? And so you can see the x's cancel out, the iy's don't, and we get 1 over 2i times 2iy. 2i's cancel out, and we get just y, which is indeed the imaginary part of z, right? Okay. What about the real part? We don't need the real part, but what would you do to get the real part?
1/2 times z plus z star.
Yep. So very similar proof here, which we're not going to do. Okay. Okay, well, we're going to use the imaginary part 1. Okay. So let's let z. So let our complex number be this f, this inner product of f with g. Remember what f and g are from up here. Okay. And therefore z star is equal to gf, right? G inner product with f, right? We've done this, we've proven that before. Okay, and so therefore we can use this inequality to write down sigma a squared sigma b squared is greater than or equal to the square of the imaginary part, which is this 1 over 2i, f inner product with g, which is our z, minus g inner product with f, which is our z star, squared. Okay, that's from our inequality. So that's, you can see we're starting to narrow in on something that might look like this, right? We got an inequality at the very least. Now we just have to calculate these guys. Okay, we have to calculate these inner products. So I'm going to use a different color. I'm going to look for FG. Okay, so now I can, reconstitute my my F's and G's here, because I'm going to need to know what they are. So my F is this guy, and my G is this guy. Okay, so I have the F, which is the A hat minus the expectation value of A, acting on psi, inner product with G, which is the B one, right? So it's the B hat minus its expectation value, acting on psi. Okay. All right. So now we just need to manipulate this. So let's just keep going. I'm now going to bring this guy. This is from Michigan. I'm going to bring this back over this side. Okay. So we have the sorry, this is psi now. Just give me a second. So we have psi on this side, and then we have the A hat minus the expectation value of A, acting on the B hat minus the expectation value of B, acting on that psi. And I've got to be careful to not put it, I wouldn't, you can't just switch it up, meaning I couldn't, if I'm putting this onto the other side, if I'm putting this A hat minus expectation value of A on the other side, I can't switch the order, right? I can't put it in front of psi, because I don't know if these operators commute or not. So I gotta be careful. Okay. All right. Fine. So now I'm going to be very careful, and I'm going to multiply this out. So I'm going to get, on one hand, we have psi, and then I have A hat, B hat. Right, and then I have A hat times, or negative A hat times the expectation value of B. I don't have to worry about the order there, because B, the expectation value of B is like a number, just a number, right? Like 3. So A hat times the expectation value of B. And then I have the minus expectation value of A times B hat. I don't have to worry about the order there either. So minus expectation value of A, but I'm not moving the order. I'm just saying I don't have to move. I don't have to worry about it. Okay. And then I have the two expectation values. So I get positive expectation value of A, expectation value of B, and then I have my psi, and then I have a bracket ending. Sorry, I got a little squished. Okay. All right, fine. So now I'm going to split this up into a bunch of different, expectation values. So I have this is equal to psi expectation value of AB. And then, sorry, I forgot about the last part there. There we go. And then minus, I'm going to pull out the expectation value of B because it's just a number. And now I have here the expectation value of A. I'm just not writing it like expectation value, but that's what it is, right? That's what this is. And this is the expectation value of AB. Okay, and then minus pulling out the expectation value of A. And then this is, of course, now the expectation value of B. Okay, plus pulling out both of the expectation values, and then I just have the inner product of psi with itself. This is going to be 1 because remember psi is normalized, right? This is 1. Okay. All right, so what do I have? Well, I'm going to write this now in terms of expectation value notation. So the expectation value of AB. And then I have minus B, expectation value of B, expectation value of A, right? And then I have minus expectation value of A, expectation value of B. And I can combine these terms in a minute, I will. Plus, oh, well, I have another term. Expectation value of A, expectation value of B, right? And so I'm end up with expectation value of A times B, right? And then minus expectation value of A, expectation value of B, right? So far, so good. Okay. So now, if we did the other one, so if we do G, so we have to now do, this one, GF. I want you guys to do this one. Okay. And I'm going to put you in, give you a second to copy things down. Okay. So do you have everything in your notes? Still going, Jackson? I'm going to put you in some breakout rooms for the last part of class here. Well, actually, hopefully it won't take you that long to calculate G on F. But I'm going to give you a second to get everything down. Let me a thumbs up when you're ready for breakout room. Okay, you're going to be calculating G on F, right? Okay. Now, I need a shout out from Jeff, Dylan, and Andrew to make sure you guys are here and ready to go into breakout rooms. Hello?
Here.
Andrew, okay. Jeff and Dylan?
Yeah.
Okay, great. Dylan? Hello?
He said here in the chat.
Oh, I didn't see it. Okay, sorry. Thank you. All right, so, and did I already get a okay from Jeff?
Yeah.
All right, thank you. Okay, perfect. Okay, I'm going to send you guys into breakout rooms. I'm going to stop the share, so make sure you have everything down. You do? Somebody else in your group should anyway if you don't. Okay. All right, so going into breakout rooms. Let's see. I'm going to put Yeah, I'll put. Are there 5 of you? Yeah, I'll just get 2 rooms. Okay. Sure. Ready? Remember, you could message me from inside the breakout room. Dylan and Jackson, you got to go to the breakout room. Finny, come here.